Okay, before we talk about binomial distributions today, I just want to make sure we're happy with the ideas from um, 6.1 that we're going to need and use, particularly expected value and average value. So just real quick, go through these and see how you would want to respond to these 4 questions. And then we'll talk about them. So I'll give you another couple of minutes to play with these in case you're just getting settled in. Um, if you have any questions in the interim, let me know. So for that first question, is this a valid probability distribution? Hopefully it is, or the rest of these questions aren't valid questions. But I did put A and B under that valid probability distribution. There are two, you may remember there are 2 qualities or 2 restrictions, 2 things that have to be true for a probability distribution to be valid. So remind yourself what those 2 things are. The other 3 are just kind of computations based on our table. So this supposed probability distribution is just one that I found. It wasn't actually even for the number of cats. I made that up as a just to have us have a random variable we can actually look at. So don't take these probabilities to heart. Uh, Probably fairly inaccurate for cats in a household, but that's okay. This is our number of cats in a household in a particular community. We'll go with that. But 2 things had to be true for a probability distribution to be valid. Anybody want to remind us what those 2 things were? Alan, you said it had to equal 1 I would say what has to equal 1, but what has to equal 1 is the sum of all those probabilities. So if we added these all up, they'd better equal 1, or really close to. Sometimes if there's rounding involved, you might get 0.9998 or 1.0001 if there's some weird rounding going on in there. But these should, other than for rounding, equal up to 1. So if we wanted to verify that, we'd have to literally add these all together. And I suppose we could do that to be what, 10, 20, 30, and then 10. I don't want to add all those up. But if we did add all those up, presumably they would add up to 1. So that's our first check. The sum of the P of X's, the probability of the individual events, must equal 1. In a lot of ways, that's the big qualifier. The other qualifier, it's just as important, but it's not as common for it to be an issue. What is the other qualifier? What has to be true about all those probabilities? Allie, yeah, each individual probability has to be, we often just say less than 1, but it also certainly does have to be positive. So the probabilities, each individual one of them has to be less than 1 and positive. So you can't have a negative probability. You can't have a probability greater than 1, greater than 100%. So all of those things have to be less than 1, and they have to add up to 1. Now, if I wrote a probability distribution, say had a negative on that one, and this one was, 1.24 or 124% chance of having 3 cats, you'd probably look at that and go, well, that's weird, not right. But oftentimes when asked, is it satisfying, or show that it's satisfying the requirements for a probability distribution, often people kind of will forget what those are, even though, well, yeah, we know they're less than 1. Yeah, we know they add up to 1. Those are the restrictions that you're being asked for, or to show, or to just mention when you're being asked if a probability distribution is valid. So questions about that? Probability that a household will have at least 3 cats. 6-1 and 6-2. I don't remember which one it is, but a chart in 6-1 or 6-2 talks about the at least, at most language. It does tend to get people sometimes, mostly because it always, not always, but often seems backwards. So if we're talking about having at least 3 cats, at least means that is the smallest, lowest number you'll have. So at least 3 cats would be 3 cats or 4 cats. So if you have at least 3 cats, you got a lot of cats. Now, it depends on how you feel about cats, I suppose. Seems like a lot of cats to me. So if we want to know the probability of having at least 3 cats, that's the probability that you have 3 or 4 cats. What did we do with probabilities when we had an or?
Add them.
Add them. Good. So it's the probability of our 3 plus the probability of our 4. So it's going to be the 0.2468 plus the 0.2975, which is going to give us about, what, 54%-ish. I'm rounding here. When we're given an at most, oftentimes when people say at most, they want things to be large, and that's, at most should respond to that. But at most 2 means that 2 is the upper bound, is the maximum. So at most 2 is 2 or 1 or 0. Like if we say, hey, if you want to live, or if you want to rent this apartment, you can have at most 2 cats. That means you don't have any cats, you're fine. You have 1 cat, you're fine. 2 cats, you're fine. More cats than that, not fine. So, or if somebody says to rent this apartment, you have to have at least 3 cats. That would be weird, because they'd be telling you have to have a lot of cats. So think of it in a context, or in a sentence in context, and it usually helps in trying to figure out which way your at least or at most have to go. But again, since it's an or, 0 or 1 or 2, we're going to add them. So again, the probability of 0 plus the probability of 1 plus the probability of 2. So add those together, and what is that, 20, 36, somewhere around 46-ish percent. Again, I'm being a little rough with that. Well, and actually, at least 3 was 54. At most 2 should be everything else. So that 46 and the 54 should add to 100%. So it looks like they do. So that's nice. So before we talk about expected value, any questions about that? No. Leslie, what about you? You doing good? Cool. Alan, how's your cat drawing coming? For this next test, you'll have to draw a picture of a cat. Doesn't have to be a good one. Okay. Expected value is a way to talk about means. So when we talk about the mean for a probability distribution, we'll often hear it called expected value. And sometimes we'll hear it called a weighted average. So if we were to kind of reword this question, what's the expected value for the number of cats in a house versus what is the average value for the what is the average value for the number of cats in a house? Those are essentially the same question. What is one value that we can put to, how many cats there are going to be? How many do we expect? The weighted average is called weighted average because it is weighted by the probabilities. So for example, if we just say added up the different possibilities, if we just found the average between 4, 3, 2, 1, and 0, just added those up, what would we get? We'd get 9 divided by 1, 2, 3, 4, 5, and say the average was 9/5. That wouldn't be taking into account the fact that there are a lot more 4s than there are 2s, and twice as many 0s as there are 1s. Not quite twice, but a lot more 0s than there are 1s. So if we just average those 4 possibilities, we would lose the fact that the probabilities are different. So we want to take that into account. We want the probability, we want the average. So we want the average of these 5 values to be weighted by how often they occur. The problem with that is we don't know how often they occur. We don't know how many households had 2 cats. We don't know how many households had 1 cat. We just know the proportion. Luckily, that's all we need to know. Excuse me. So we can think about it a couple different ways. We can imagine that all of these are percents. If this was 21%, 15%, almost 9%, 24%, and 29%, almost 30%. If those were all expressed in percents, percent essentially means per 100, right? The centi from the Latin for 100. So we could imagine we had 100 cats. That's a lot of cats. So imagine this was out of 100, or 100 cats, or 100 households. It'd be 100 households, sorry. So out of 100 households, 30 of those households had 4 cats. Out of the 100 households, 24 had 3 cats, almost 9 had 2 cats, 15 of them had 1 cat, and 21 of those households had no cats. So if we wanted to average them based on the 100, we could do that. Don't worry about this. We're not actually going to do it this way, but we could. We could have 21 zeros. 21 zeros. And then add 15 ones. 1 plus 1 plus 1 plus 1. Do that 15 times. Obviously, we're not going to do that. Well, we could, but. And then we could add 2 a whole bunch of times. How many times would we be adding the 2? Well, we'd be adding that. I'm going to round that one up to 9 times. And we could keep doing that. But that, even just writing that all out once would be a pain, right? So we're not going to do that. We would then, have to divide all that by 100, but we're not going to do that. Instead, we can shorten up these repeated additions if we want. We've got 21 zeros, so 21 times 0 would give us what that sum would be. We've got 15 ones, 9 twos, 24 about threes. I'm rounding these pretty bluntly just so we can look at it. And then 29 fours, all divided by the 100 households. So that would speed us up a lot if we wanted to. So that would take the 4 and the 2, and they're now weighted by that probability. There's now the amount of 4s we're adding together and the amount of 2s we're adding together respect how many there are, how likely they are to occur. But again, even calculating this out is a little bit irritating. So instead, if we divide that 100 into each of these terms, we'll get back to percentages. That'll be 21% or 0.2126 if we want to be exact, times 0, plus 15 over 100, that's our 15%. So if we tried to use even the formula for mean, add them all up, divide by how many we have, no matter how many we have, we know that's going to end up being 0.1536 of them, and 0.0895 of the two cats plus 0.2468 of the three cats, and 0.2975% or as a proportion of all the households will have four cats. So instead of using our normal formula for mean, add them up, divide by how many we have, essentially the probabilities have already done that. They've already looked at how many we had out of the whole. So that job has already been done. All we have to do is take the individual probabilities and multiply them by the value in question and add those up. You might remember the sigma for adding. So if we want to find the average number of cats we expect to find in a house, or the expected value, or the weighted average, whatever you want to call it, multiply the individual probabilities by those probabilities values, add them up, that'll give us our expected value. So take a minute and do that and tell me what you get. Add up all those products and see what we get for the expected number of cats in a household in this community. Let's see. Olivia, you're proposing, we got a couple different answers. We have one proposition of 2.263 and another of 2.413, and then another one of those. Those are very close. I would check, Alan, check what you typed in, make sure none of those are a little bit off. Like this is a 4, might look like a 9. That's 2, 4, 6, 8. Yeah. Yeah. Reading my writing's not always the easiest thing. That's what the chart's up here for. So a little more than 2 cats, and that should make sense on our chart. You know, even though 2 isn't very common all by itself, as an average, there's a lot less than 2. There's a lot of them that are more than 2. That's going to average out to about 2. I buy that. A little bit more than 2, that 3 is a lot more common than the 1. So when we weight those values by their probabilities, we end up with, you know, a fairly nice average. So what's the expected value for the number of cats in a household? We expect 2.263 cats. And again, because it's an average, because it's a descriptive statistic, it doesn't have to be one of our actual values. But yeah, we expect 2, maybe a little bit more cats in a house. No, you can't have part of a cat, but your expected value can be part. Because again, our averages, you might remember, like, people often say the average number of the average family has 2.3 kids. They don't have 0.3 kids, but that's where that mean ends up being. So it doesn't have to be one of our actual possible values for it to be a descriptive statistic. Short people are still whole people. I know that's hard to believe, but just because they're short doesn't mean they're not just as valid as the real people. Okay, so let's play a game. In this game, you've got to pay $1 to play. And when you pay that $1, you get to roll a 6-sided die, a fair 6-sided die. On a roll of 1, if you get a 1, you get nothing back. You lose. You get 0. So in essence, you're down $1. You're at negative $1 if you roll a 1. On a 2 through 5, you get a prize. That prize is 25 cents. So you're still down some money. You're still down 75 cents for playing the game. But you didn't lose your whole dollar. On a 6, you get $5. So you roll that 6 and you get $5. The question is this a fair, put that in quotes, game? Now, I put fair in quotes because fair, in terms of statistics and probability, does have a specific meaning. For a game to be fair, the expected outcome should be the same for both parties. So usually when you're playing a game, if you're gambling like this, usually in the long run, the odds favor the house, right? They favor the one running the game. So normally games like this, when you're gambling, games aren't fair. They favor the house. If this game was in our favor, if the odds favored us as the player, then we would expect to get out more than we pay in. So this fair game idea really is an expected value problem. If we find the expected outcome of this game is $0, that means we're going to lose as much as we gain. It's a fair game. That's almost never the case. Usually the game favors one party or the other. So if the expected value ends up being negative, then we expect to lose in the long run. If the expected value is positive, we expect to win in the long run. So my first question is just from a kind of intuition perspective. If you were to play this game for a long time, yeah, you'd more often than not, you'd lose that 75 cents, but every once in a while you'd get $5. That $5 would kind of get you back up to a good amount, and then you could keep playing. Yeah, you'll lose the 75 cents a lot, but then that $5 will boost you back up. So do you expect that $5 will keep you making money? Or do you expect that the loss of the 75 cents is going to add up to more than the $5 will pay off and you'll lose over time? What's your expectation? You think our expected value is going to be positive and it's a good game for us to play? Or do you think our expected value is negative and we're going to eventually run out of money? Without doing any math or trying any mechanics, what's your intuition say? Alan says you're going to lose, but we know Alan. Alan's pessimistic, right? Now, a 50-50 chance, I have to say a 50-50 chance of what? You mean it'll balance out over time? The odds are huge. Odds are huge for what? Odds are huge that you'll lose. Odds are huge that you'll win. So yes, it's certainly true that we will lose more often than we win. Olivia says you'll lose, and we'll certainly lose more often. You either lose the first time or maybe you get $5 your first chance, you can keep going. Well, assuming you've got a bankroll, a little bit of a bankroll anyway. So it's certainly more probable that we're going to lose. But if we can play this for a little while, if we've got enough of a bankroll to play for a while, that $5 might help us keep going. But let's say instead of $5, it was $500. So yeah, we're only going to get to 500 one out of every 6 rolls. But getting $500 every 6 rolls-ish, when it costs you $1 per roll, I would do that all day, every day. So just because it's more likely that we'll lose doesn't necessarily mean it's a bad deal, depending on how much we win when we win. Fair? So at $500, yes, do this all day. It's, call it an investment. At $50, I would still totally do it all day. At $5, I don't know. I'd want to do the math. So whether it's a fair game or not really depends on that expected value. What is our expected outcome? And just like with the cats, this expected value, it doesn't have to be one of our outcomes. We don't have to say, well, our expected outcome is to lose 75 cents. What's the expected value on a long run of plays? If we did this 100 times, what would the average end up being of how much we win versus how much we lose? So to find that, I want to make a probability distribution table like we had up above of our different possible outcomes and their probabilities of occurring. Now, this often gets to be sticky. What are the possible outcomes? So on your notes, hopefully you're making notes. You should always make notes. List out the possible things that could happen. Alley 1 through 6. That is the trap alley. That is not our list of possible outcomes. It is the trap, though. It is how a lot of people start a problem like this off on a bad foot. How many different things can happen to us as a player?
Only 3, right?
Only 3 possible outcomes. We could lose $1 if we got a 1. We could lose 75 cents, or we could gain $4. Now, Alan, win or lose, because there's multiple ways to lose, we've got to break that up. We could lose this way, or we could lose that way, or we could win. Fair? So, what is the probability that we will lose the $1? How many different rolls make us lose the $1? Well, one value out of the 6 possible outcomes have us lose the entire $1. You're right, Alan, 5 out of 6 we lose, but not all 5 out of 6 do we lose the entire $1. We only lose the entire $1 1 out of every 6 times. How many times do we lose just the 75 cents? 4 out of 6. Okay. So on the 2, 3, 4, or 5, 4 out of the 6 rolls, we lose 75 cents. What's the probability that we win $4? Olivia, Allie, Leslie, Allie, 1 out of 6. Yeah, 1 out of the 6 possible rolls. Are we going to win the $4? So, Allie, that's where your 1 through 6 comes in to generate our 3 possible outcomes. Now, we could write those as percentages if you wanted to. See, 1/6 is 0.1667. So we could write those out as decimals if you wanted to, but I don't want to. So of these 3, which outcome has the most weight to it? Well, the losing 75 cents has the most weight to it because it has the highest probability. Winning $4 and losing the entire $1 have lower probability, so they have lower weight. So when we average these 3 possible results, we don't want to average them as if they have the same weight. We want to average them respecting their probabilities. So instead of adding them together and dividing by the 3, we're going to multiply them by their probabilities. The 1 out of 6 losing dollars we have, the 4 out of 6 losing 75 cents we have, and the 1 out of 6 losing $4 that we have. A little inconsistent there with my parentheses. $4, 1 out of 6. Just to put the same thing in parentheses each time. So again, this is expected value because it's what we expect our outcomes to be on the long run. It's called a weighted average because we're averaging things weighted by their probabilities. And it's a mean because technically we're adding them up and dividing by how many. We're just using the probabilities to tell us what that how many is. So compute that real quick. Tell me what you get. Anybody else get zero?
I just put it in the same time you said that.
So yeah, the expected value is 0. Now, are we ever going to get 0 on this? No, we're either going to lose $1, lose 75 cents, or make $4. We're never going to give our dollar away and then get $1 back and come out even. But in the long run, if we did this game over and over and over and over again, we're going to average out to having won as much as we lose as much as we win. We're going to end up with 0. No overall change. Alan, you said error. Was that error from the fraction work or error from putting that into the calculator, or did I lose you someplace else? Calculator? So that would depend on how you put it in. That's why fractions are nice. So just as an example, this is how the lottery gets you. When you play the lottery, you either lose your dollar. There's usually a fairly, a lot of little sub games where you might make $10,000. And then there's, the big prize. Let's say the big prize is $100 million. And people go, oh my gosh, $100 million. $100 million is a crazy huge amount of money. But we have to look at that in terms of the probabilities. So the probability that you will just lose your dollar and go home with nothing is usually huge. The probability that you'll get 10,000, people win the 10,000 every once in a while. They've got to keep people on the hook. Well, it's usually not even that good, frankly. Chance of getting the 100 million, 0.00000000006. So a tiny probability that you'll get that $100 million. So if we wanted to find our expected value, well, what's the average between 100 million, 10,000, and -1? The average between those is a massive amount. Does that mean if you play the lottery on average, you'll make that massive amount? Certainly not. And not because we have to weight those by their probabilities. So the -1 times 0.99998 plus the 10,000 times its probability 0.000019994 plus the grand prize of 100 million times 0.000000006. If you add all those up, you'll get the expected value. How much do you expect to get back for your dollar on average in a long run of playing the lottery? So calculate that real quick. Don't play the lottery, by the way. It's a horrible, horrible thing.
Waste money.
It's a complete waste of money.
And time.
You have a higher chance, and this is true, you have a higher chance of being saved from a bear attack because the bear is hit by a car. It is a higher probability that that will happen to you than you'll win the lottery. You have a higher probability of being hit by lightning within 7 seconds of leaving the store than winning the lottery, even if it's a clear day. It's a voluntary tax on the underprivileged by selling them hope. It's horrible. It's a vile, vile, vicious thing. That's my editorial for the day. Those opinions do not necessarily reflect the opinions of the math department and RCC as a whole, but don't play the lottery. It's evil. But it helps fund schools. Yeah, it helps fund schools by not taxing the people who have money to tax because they can pay. Yeah, it's horrible. It's horrible. Don't play the lottery. Anyway, what happens when you add all that up? Negative, that seems about right. Negative 0.739986. So that means you lose 75 cents out of your dollar if you play over and over and over and over again. Even if you win every once in a while, like a lot of the lotteries have that, you win $5 here, $10 there, a couple bucks there. Even with all those, if you play it for the long run, you are just paying into a system. Now, are you ever going to actually, get, was that 26.1 cents back? No. But in the long run, your winnings and losings are going to add up to you lost 73 cents for every dollar you put in. Fair? Is that experience talking? No, it's not. It's math talking. And that's actually one of the reasons why taking classes like this, that while studying probability and statistics is so important. You spend a tremendous amount of time out in the world being subjected to deals, to odds, to choices, to data. And believe me, the people who are trying to get your money, your time, your attention, they know how the math works. And they're trying to make money off the fact that they know how the math works, and most people don't. Fair? So the more armed we can be with, when something says, 50%, get 50% more, knowing what that means. I love when things say 50% more, because they don't say 50% more than what? 50% more than you would get otherwise, 50% more than they used to give you. There's a company, it was a toothpaste company that advertised their toothpaste as you get 50% more product in their tube of toothpaste. So it had, a big, and you've seen that in your bottles, it'll have a thing on the side that says 50% more. And they got sued because it was 50% more than the 33% reduction that they gave. So they took the product, they reduced its volume by 33%, and then increased that by 50% and said, you're getting 50% more. And that was legal because they didn't say 50% more than what? They got sued, but they won. People who sued them lost because they didn't say what it was 50% more than. It's essentially a meaningless statement. So be armed. So, questions about this expected value. It really is just an average, and it really is just as nice as take the probabilities, multiply by the values, add them up. And boom, you get expected value. Alan, why are you talking about my car, my house, and my marriage? No. Okay. Now, briefly, to give us a preview of 6.2, in 6.2, we're starting to talk about one of our big things, one of our big tools. As we go on in the course, we will generally have two types of problems. One of those types of problems will be binomial distributions. The other type of problem will be, well, not binomial distributions. We'll get to that in chapter 7. So binomial distributions, the bi in binomial means there are two choices. So binomial distributions describe events where there are two possible outcomes. We often think of those two outcomes as essentially a success or a failure. You could also say, one of them is an answer of yes, the other one is an answer of no. Sometimes we assign the yes or the positive outcome a 1 and the negative outcome, the no, I'm a 0. But they could be anything. They could be black versus white. They could be, Republican versus Democrat. You got to be careful with Republican versus Democrat because there are people that are other, but, did you, anything, employed versus unemployed. So anytime there's two choices, we are in a binomial distribution. We will often default just talking about success or failure, yes or no, even if there's no, benefit one way or the other, even if it's not, Research's not working, even if it's not like one is a positive outcome and the other is a negative outcome, we'll often just break them up into, we're going to call success this, or we're going to call yes this, like if you had just, I like dogs versus I like cats, assuming those are your only two choices, it's a binomial distribution. We'll label one of them as a yes or a success, the other one as a failure or a no, just for convenience. Fair? So when we talk about binomial distributions, we really talk about the proportion of successes versus failures. So in a binomial distribution, the big thing we're going to care about is the probability of our successful results. So the probability of a yes, essentially. So I don't want to write it that way. So the probability of success, we will generally label it with a lowercase p. And let's say for this example, we're going to look at the probability of getting that success is 0.6. So 60% of the time we get a yes, we get a success, we get whatever we're calling the yes result for our distribution. So that proportion is what's going to define how many, or going to define our probability distribution. Now, the variable that we study in binomial distributions isn't yeses and nos, it is the number of yeses, the number of successes in n trials. So the question up above here with the cats, this is not a binomial distribution because our variable isn't how many yeses and nos we have. Our variable is a number of cats. 1 cat, 2 cats, 3 cats, 4 cats. For a binomial distribution, think of things like, another example I forgot, classic one, heads and tails. So imagine you flip a coin 10 times. That's our n trials. What is the probability that we get, say, 7 heads, that would be a binomial distribution problem. Flipping a coin has only 2 possible outcomes, heads and tails. We know the probability of success, the probability of getting what we're going to call success, heads. Probability of success is 0.5 or 50%. And we're asking, what is the probability of getting 7 of those heads out of 10? So our variable is not yes versus no, success versus failure, dog versus cat, head versus tail. Our variable is how many successes out of a given number of trials. Fair? So let's look at an example. Let's go with coins, and 10's actually a lot. So just to, I know you guys have to go here in a second, but let's say we flip, let's just say 2 coins. So we know the probability of getting a success is 0.5 because they're same probability or same likelihood of getting a head versus a tail. And if we want to find the probability that we get 2 heads, so 2 successes, one of the ways to do that is just to diagram it out. We've got 2 trials that we're running, and what kinds of things could happen? Well, we could get tails both times. We could get a tail on the first one, a head on the second one, a head on the first one, a tail on the second one. Or we could get 2 heads. So of those 4 possible outcomes, 4 possibles, how many satisfy our condition? How many times did we get 2 heads or 2 successes out of those 2 trials? Well, it only happened once. So probability of getting 2 heads, it only can happen one way out of the 4 possible things that can happen. So the probability of getting 2 heads, 1 out of 4, or 0.25, or 25%. Does that seem reasonable? Now, the reason that this gets more difficult, the reason we're going to need some tools, is what if it was even just 3 coins and we wanted to know the probability of getting 2 heads, or really we're going to call heads successes, probability of getting 2 successes. Well, if we wanted to do it with 3 coins, we would have to write out every possible way that we can get, or every possible outcome with flipping 3 coins. So it could be, tails, tails, tails. It could be heads, tails, tails. It can be tails, heads, tails. It can be tails, tails, heads. It can be, there's a bunch of them. We'd have to write out all of them. Heads, heads, tails, heads, tails, heads, tails, heads, 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 heads. How many is that? 1, 2, 3, 4, 5, 6, 7, 8. We'd have to write out all of them and figure out how many have 2 heads. Well, that one has 2 heads, that one has 2 heads, and that one has 2 heads. So what's the probability of getting 2 heads? 3 out of 8. That was a lot more irritating, right? Just because there are more possibilities. Well, imagine if we flipped 10 coins. How many different ways can we arrange T's and H's in 10 slots? A lot, and I don't want to do it by hand. So we're going to need a tool that's going to control how many possible ways we can do things. And luckily, yesterday we talked about that. Remember our factorial discussion? on figuring out how many ways we can arrange things. So we're going to use factorials to figure out how many ways we can arrange what we want versus how many ways can we arrange what's going to happen, and build a nice tool for finding these probabilities. So that's just a little introduction. That's what our conversation tomorrow is going to look like.
Okay, thank you.
Sure. Anything you guys need before I let you go today? Okay, go look over 6.2 so we can be all ready and happy for that discussion tomorrow. And have a wonderful day.
Thank you. Bye.
Bye-bye. Bye, Alan. Allie.